Well, today marks the starting of the chapter on closed operators. But in order to do that, I would need to prove a proposition from the chapter on Hahn-Banach theorem, because eventually we would need these kind of results at a later point of time. So the technique which is used here is something new, and we would use these kind of techniques in our further proofs too. And thus, let's continue. So let x and y be norm spaces and y be finite dimensional. Any surjective linear transformation from x to y is open. That is, it maps open sets in x to open sets in y. So the essential idea is that if I take a, let me put it this way, that if I take an open ball in x, it is mapped to an open ball in y. So the whole open set is mapped to an open set. So we would come to this point a bit further. So x and y, maybe I colored this. Anyway, so now let's have a quick look. So let fx1 to fxn be basis for y. Now, if this was like an elementary course, then I would say let y1 up to yn be basis for y. Since we know that y is surjective, therefore for every x belong to x. Since we know f is surjective, therefore there exists x belong to x such that f of x equals to y. Thus, we can say that fx1 to fxn be basis for y. And now I define the norm of y as the sup norm. So I write it as the max of norm of alpha I such that y is written in this way. So this is just a linear combination of its basis. Now choose s greater than 0 such that the important part is here to look is that he's saying choose. It's my choice. So I choose my s such that this condition is satisfied. Now, note that now when I write this linear combination of Tix's, it belongs to the ball of radius 1 centered at 0. And the condition is that all the norms of Ti's is less than equal to s. Now, why this ball belongs here? Well, we can just check it. I just take the norm on both sides, and here's the triangle inequality in this step. And here I see that, okay, I can take the s out, and I see that the norm is less than 1. So thus this element lies in the ball of radius 1. So now if I apply f on both sides, or f on this and f on that, so this just becomes f b10 and this becomes this. Now this, I take the t outside, f is linear, it looks like this, and it's just the same from here. Now the interesting part comes. Now if you look at the ball of, now let me specify this is space y. Space y. So in my space y, if I have a ball of radius s, it consists of all such y's such that y is written like this. The max of the alpha i's is less than s. Now I know that this ball is a subset of fp10 because if you see, now this ball is a set and this set consists of all such elements whose shape look like this. But I know that all such elements or vectors in my space y belongs to fp10. So this is that an element belongs to this set, and now I say that okay, this is a collection of elements, and thus I write this as a subset of this, because if one element belongs to it, then the subset which consists of all such elements must be a subset of this. So this argument is also pretty much very straight. Now the final crux comes, and that is this: let u be an open subset of x. We want to prove that f of u is an open subset of y. And the way I do it, let for every value of x belong to u, there exists r greater than 0 such that the ball of radius r around x completely lies within u. And now if I can prove that if I make f of x, then that lies completely within f of u, then I can say that okay, if I take f of x and it lies is a subset of f of u, this ball, well, let me show it this way. Let's continue piece by piece. So I take an x, I draw a ball around it, and I say that it is in u, and now I write this as this. And now if you If you just apply f on both sides, so if I just apply f here, then it becomes rfb10, rfb10, and f of x, which is a subset of f of u. And then I write this thing here as this. But now I see that f of x plus rbs of c is a subset of f of x plus r. Rather than using b as 0, I use fb10 because of this relation here. But I know that now this is a subset of f of u. So I can draw a ball of radius rs around my f of x, and thus it maps open sets in x to open sets in y. And this finishes our proof.
So now we start with operator theory. It's the 4th chapter. And let's jump directly into the lemma, that's Skander's intersection theorem. Now let X be a norm space, and we say that the space is complete if and only if it holds this property. And what is the property? So I have a sequence of bounded, closed, and non-empty sets with the property such that A1 is a subset of A2, is a subset of A3. So no, the other way around. So A2 is a subset of A1, A3 is a subset of A2, and so on, and so on. And the diameter of AJ, which means the diameter of any set, and J is the index. Now the diameter tends to 0. And what is diameter? The maximum distance between 2 points on the set. Now this tends to 0 as J tends to 0, and it consists of precisely one point A, such that, so what it is saying is, if I take the intersection of all such sets from J equals to 1 to infinity, then it will contain precisely one point. If this condition holds, then I can say that my space X is complete, and if my space X is complete, then this condition holds. So that's Skander's intersection theorem, that the intersection of a sequence of bounded, closed, non-empty sets with the properties such that they are contained within each other. The successive sets are the subsets of the previous sets, and the diameter of the set tends to 0 as J tends to infinity. And now the intersection consists of precisely one point. So if I take the intersection on every bounded, closed, non-empty set which satisfies this property, and that intersection consists of precisely one point A, then I say that my space is complete. So that was Skander's intersection theorem. Again, 30-second summary. The intersection of bounded, closed, non-empty sets which satisfy this property consists of precisely one point. If this is the case, then X is complete, and if X is complete, then this holds true. Now we have Bayes' theorem. So Bayes' theorem says that let X be a Banach space and AI be a sequence of closed subsets of X. So there I had closed, non-empty, and bounded. Here I have closed subsets with the property that the interior of the union is non-empty. Now if this is so, then there exists a K belonging to N such that the interior of K is non-empty. So this Bayes' theorem is pretty intuitive. So of course, if I have my space X, which can be written as the union of closed subsets of X, and I say that the interior is non-empty. So what do I mean the interior? So well, if I have X as my norm space and Y is a subset of X, so by interior of Y I mean the set of all interior points of Y is called the interior of Y. And I say that what are those interior points? So in space Y, so let me draw a small picture. So here I have my space Y. Now what do I mean by interior of Y? So by interior of Y is the set of all interior points. And when do I call a point an interior point of Y? That is when, if around that point I can draw a ball of radius R, and that ball completely lies within y, then I say that this point is an interior point of y. And y is open if every point is an interior point of y. And the only important thing is that the ball that I'm drawing is in space x, because x was a Banach space or a norm space. So ball that I draw is always in space x, but it should lie completely within y. So for that to be an interior point, so always of course I cannot draw a ball in a set. I can always construct a ball in a space. So y is a subset. I construct a ball in x and I see that the ball lies completely in y. So I say that okay, this point is an interior point of y. And if every point is interior point, then y is open. So now we come to uniform boundedness principle. What does it say? It's a very important theorem and you need to understand it very clearly. So let X be a Banach space, Y a norm space, and Ti a family of bounded linear operators from X to Y. It follows from this that supremum over all I belonging to capital I, supremum over the family of operators is less than infinity, that this supremum is also less than infinity. So what it is trying to say is that pointwise boundedness implies uniform boundedness. That's the mantra here. Now first we'll go the other way around just for fun. So we'll say that okay, suppose that norm of t is less than infinity. We'd like to show that norm of tix is also less than infinity for each fixed x. So fix x and note that norm of tix is always less than equals to norm of ti, norm of x, and therefore if you apply supremum over both sides, then supremum over norm of tix is less than supremum over norm of ti, norm of x, which is of course less than infinity. So here to here is understood. Now we go from this to this. Now define an an which is a closed subset. I would prove I am defining a subset an of x such that an consists of all such x such that the supremum over the family of I is less than n, less than or equal to n. And so this set an, so we have like this different sets for like a1, a2, a3, and now it follows from the continuity of ti that an is closed. What does it mean? So what it means is that supremum over norm of ti x is less than equal to n if and only if this statement holds, that norm of ti x less than equals to n for all I belong to capital I. And one thing of importance here is that this supremum is, let me use the same pen, this supremum is over the family of I. So if the supremum of norm of tix is less than equal to n, if and only if norm of tix is less than equal to n for every I belonging to capital I. So take a sequence xm in an. So I had this set an that I constructed here. This is an, and in this an I take a sequence xm such that xm tends to x. Now I want to prove that x also belongs to an, because if I can prove that x belongs to an, then I can prove that this an is closed. So let's see how we would do these. So I say that okay, xm belongs to an if and only if supremum over I tixm is less than equal to n, because that was the definition of what does it mean that, if I write that definition, yeah, that's the exactly definition. Now if and only if norm of tixm less than equal to n for all I belong to capital I. Now take limits on both sides. Which side? On this side and this side. So limit m tending to infinity and limit m tending to infinity. But since here is n, so this will remain the same. And now I take the limit inside the norm, and then I take the limit inside t, because the norm is continuous and t is also continuous, bounded. So t is also continuous. So I can take that limit inside, and thus once I take that limit inside, I see that limit m tending to infinity xm is equals to x. So I can replace this with x, and thus it's less than equal to n for each I belong to capital I. But as soon as I do that, my problem is solved, because if this is the case, then if I apply supremum, no, it's just not even applying supremum, just this step to this step. This step is if and only if this, and this is where I make use of the definition of what it means for any x to belong to an. For any x belonging to an, this was exactly the situation or condition it needs to prove, and thus x is an. So therefore I have written there that it follows from the continuity of ti that an is closed, and by hypothesis the union from n equals to 1 to infinity an is equals to x. So these are the two things that I have. Now in order to apply Bayes' theorem, this was the condition that I needed, and another condition that was needed was that an be closed. So if I remember Bayes' theorem correctly, it was that let an be a sequence of closed subsets of x. So yeah, let ai be a sequence of closed subsets of x. So in our case it's closed, with the property that the union of ai I equal to 1 to infinity equals to x. This is also in our case. And then it says that if this is non-empty, then there exists a k such that a k interior is non-empty. So when I say that a k interior is non-empty, it means that it has an interior point. Now an interior point means that I can draw a ball of radius epsilon around it. So if I come back, I see that according to Bayes' theorem, there exists n star belonging to capital N such that a n star has an interior point A, and there exists epsilon greater than 0. Because it has an interior point, I can use this epsilon ball notation, that there exists an epsilon greater than 0 such that the ball of radius epsilon centered around A is completely contained within a n star. Now the ball of radius epsilon around A is the set of all points a plus epsilon x such that norm of x is less than 1. This is exactly what it means. Now if this is the case, then this point is in a n star, meaning that ti of a plus epsilon x is less than equals to n star for all I belong to capital I and x with norm of x equals to 1. It is norm of x less than equal to 1. This is exactly what it says here. So till here also no problem. And now I just flip it. I multiply epsilon inside, and I see that ti epsilon x plus ti, and then I use this inequality, and I get from here that epsilon times of norm of tix is less than equals to this quantity here. Now make use of this result later. So I make a small, I'll make use of this later. And now I define, I know that the norm of ti is supremum over all x less than equal to 1 norm of tix. Now this is less than equal to, if I see this, is less than equal to this, because from exactly from here, and then I can further estimate it, and I can say that the norm of ti is bounded by this quantity, and for all I belong to capital I, and thus I can say that norm of ti is also bounded. So let's have a quick recap. What we did was, we had a Banach space, Y was a norm space, and we had pointwise boundedness. We proved uniform boundedness. How did we do that? We defined a set an such that we could make use of Bayes theorem, and using that we showed that there could be a ball of radius epsilon around a point A, and thus we came to this result. We got an estimate of epsilon norm of Tix, and using this estimate we therefore estimated that norm of Ti is also less than equal to some quantity, is also bounded for all I. In this final section I would prove that norm is a continuous operator. So this norm as a function is continuous. Now T is continuous from x to y means that x and y be norm spaces that take x belong to x and epsilon greater than 0. Now there exists delta greater than 0 such that norm of x minus z less than delta implies that norm of tx minus tc is less than epsilon. So this is the definition of continuity, and I'm very careful with how I have set it up. And now claim is that with y is equals to r, the real number line, the norm, that is t, which is my operator here, is continuous. So now I see that I want to prove that norm of x minus z less than delta implies that norm of x minus norm of c is less than epsilon. So what's happening is, if I take an x, okay, and an epsilon greater than 0, I can find a delta. So if you look at the reverse triangle inequality, this is the reverse triangle inequality, and I take my delta to be epsilon. So norm of x minus z, if it is less than epsilon, then using the reverse triangle inequality I can say that the norm of x minus norm of z is definitely less than epsilon, because what I wanted to prove was, if this is less than delta, so in this case my delta is epsilon, then the implication is that this is also less than some epsilon. But this is the result which I know holds true because of the reverse triangle inequality. So let's look at it again. So what I did, what the smartest part in the whole process was, I took my delta to be epsilon, because when I take this delta equals to epsilon, and then if I look at this equation that norm of x minus z is less than epsilon, then of course the norm of x minus norm of z has to be less than epsilon because of reverse triangle inequality. So this statement here implies that this is less than epsilon. So yeah, I found this delta, and thus norm is continuous as an operator.